That leads us to Harry Hess in World War II. He was in the Navy and a ship captain, and he was mapping the sea floor. He used an echo sounder, so the ship would let out a sound from it, and that sound would bounce off the sea floor. Knowing the velocity of sound in water and the time it took for that sound to bounce down to the sea floor and back up again, Harry has mapped much of our sea floor under his command during World War II. So this is the way if you use a depth finder in a boat these days or a fish finder, it's that kind of technology. He found an intriguing topography under our ocean basins. Dun dun dun. He found that in the center of our ocean basins were mountain chains. This mountain chain here, here's North Carolina over here. We are there. There's the beach. Halfway to Africa, there is what's called a mid-ocean ridge. He detected that mountain chain. It's now known as the Mid-Atlantic Ridge. So the ocean basins had topography. Here is a cross section through going from North America to Africa. The edge of the continental margins, these are passive continental margins where they're not at plate boundaries. The center of the ocean basin is the mid-ocean ridge. It has an axis to it, just designating the center. On either side of the mid-ocean ridge are the abyssal plains, the deep depths of the ocean basins. Ah, this was big information at that time. Here is a map of the seafloor that was made from data that was collected from World War II up into the 70s. And this is a famous map put out by Marie Tharp and Bruce Henson, and it shows the amazing amount of topography of the seafloor, where these are those mid-ocean ridges. They are offset. See how there's those lines through them by transform faults. It's just a shear zone through the mid-ocean ridges. That's why it looks kind of like stair steps there and over here. On the edges of the ocean basins, especially the ring of fire around the Pacific, are trenches, really deep trenches, showing where there are subduction zones. Okay, so here is a map, kind of a cartoon then, of the seafloor. Put myself down here. The seafloor is not flat, but has ridges, trenches, seamount chains, and fracture zones. Fracture zones are those that offset the mid-ocean ridges. The deep trenches here, like the Aleutian. Over here is the Mariana, the Japan, the Kuril, the Philippine, the Java Trench. Those are marking places where there is subduction zones. So Harry Hess built on Alfred Wegener's theory of continental drift, and now we have a mechanism for the continents to move. On the top here is the early thought of what drives that tectonic motion is that we have hot rocks here in the asthenosphere by the core. Well, that would be the mesosphere. They go up into the asthenosphere, and we'll just say the mantle. And then the cooler rocks, as they reach the surface, are going to fall back down towards the core and then go back up as they get hot. Essentially, we have convection. Hot material rises and cool material sinks. This is called adiabatic convection if you're studying physics. So here's what it looks like for plate tectonics, is that at those mid-ocean ridges, then the plates are moving apart and magma is coming up into that rift valley of the mid-ocean ridge. On the edges of some ocean basins, then here's a trench. That cold, dense old oceanic crust is going to sink down back into the mantle. So that is our subduction zone. When that happens, there's going to be melt of the rocks as that oceanic crust carries water with it down into the heat of the mantle. That is going to promote melting, and when it melts, then we have a chain of volcanoes like the Andes. Here's an andesitic volcano like the Andes. Okay, we're going to look at all the different kinds of boundaries. All right, so now we have evidence for crustal motion. There are earthquakes that are at the plate boundaries. There is heat flow at the plate boundaries. We can look at the age of sediment in our ocean basins and the thickness of that sediment, and also paleomagnetism, looking at the signature in the rocks of what the orientation of the Earth's magnetic field is at that time. So here's the distribution of earthquake epicenters. These are earthquakes on the bottom, deeper than 100 kilometers. At the top, shallow ones. Shallow earthquakes are going to occur at mid-ocean ridges and at some of our subduction zones and convergent places where two continents are coming together, like around Asia. Okay, and then these deeper earthquakes are at subduction zones where that oceanic crust is getting carried down into the mantle. So we can take a pencil and do kind of dot to dots on here and outline the plates of plate tectonics using the earthquakes. Heat flow, so there's high heat. I'm going to turn my face off here. There's high heat flow along the mid-ocean ridges. We can detect that heat flow and map it out and see indeed there is magma coming up into those mid-ocean ridges. On the right here, sediment thickness and age. And the figure on the left is the continent, and come across the ocean basin here, sea level. Take a ride across the sea to the oceanic ridge, the mid-ocean ridge. At the ridge is going to be fresh, exposed, brand new basalt forming oceanic crust. And as you go away from the ridge at A, B, C, D, the sediments are going to get progressively thicker because that oceanic basalt has been exposed to dying sharks, wind-blown clays, any kind of sediment that can come into the ocean basin. The older the oceanic basalt, the longer it's exposed, the more sediment is going to be on top of it. So sediment gets thicker away from the ridge. Paleomagnetism. This is a good one. So the Earth has a magnetic field, which is a good thing. It helps keep solar rays away from us, deflects those rays, and gives us the aurora borealis. It also is recorded when rocks crystallize that have iron in them. Iron is going to crystallize from a magma in those basalts of the oceanic crust oriented to the Earth's magnetic field. And sometimes the Earth's magnetic field is normal, bottom left corner, like it is today, north is north. Sometimes the Earth's magnetic field flips. That's called a reversal. Okay. On the right side here is the magnetic polarity time scale, and it's plotted along with age and millions of years. So on this time scale, these different colors here in black are showing positives and negatives, normal time and reversal time of the polarity of the Earth's magnetic field. If we take a ship, here's another ship, and it's going to pull a magnetometer across the surface of the ocean, that magnetometer can detect the strength of the magnetic field. And so sometimes it's positive, sometimes it's negative, and that marks those anomalies in the flipping of the Earth's magnetic field. Now, if we go down to the ocean and look at the rocks, the basalt of the oceanic crust, they found out that the reversals of the magnetic field are recorded in the rocks symmetrically across the ridge. So let's say time 1, these rocks are forming in the volcanoes of the mid-ocean ridge. Time 2, they've moved away. Time 3, they've moved further away. Time 4, they've moved further away, symmetrically across the ridge. We can map that across the ocean basins and see, oh my gosh, the age of the Earth's oceanic crust is symmetrical across the ridge. That is where we're making bigger ocean basins. They're spreading apart at those mid-ocean ridges. So here is a map showing the ages of ocean basins and what that looks like over time for our ocean basins. So red on here is brand new rocks forming at the mid-ocean ridges, and the edges of those ocean basins that are blue are the very old oceanic crust.